Welcome to the Chapter 9 Part 1 video. This is starting with 9.1, 9.2, and 9.3. Chapter 9 focuses on what are called transformations, which are movements. They're changes to an object. And 9.1 is specifically focusing on translations. Now, in language, translation usually means changing a word from one language to another or changing a concept from one language to another. In math, translation is moving something from one place to another. So our objectives for this section are to identify a rigid motion. A rigid motion is a motion or a movement that doesn't change the object. So it's rigid, it stays the same, but it moves somewhere. And specifically to find the translation images of figures. So that's our goals for this section. Transformations are not just used in math. In computer animations, so for like TV, a lot of times what they'll do is they'll take an image and they'll repeat it. So they'll just kind of copy and paste and make slight adjustments for perspective and things like that. But really what they're doing is they're applying these ideas of transformations. So a couple of terms that we need to know in order to continue with talking about transformations are the image from before the original image, and that's called the pre-image, the original. And then the image from after, and that's called the image. So the result is the image. Another way to think of this is before and after. Okay, now we were talking about this word rigid motion preserves size and shape. So it's staying the same size and the same shape. In our two images here, you can see these little tiny people and the bigger person. Those are different sizes, or the dog and the person are different shapes, also different sizes. But we have this picture of the two twins here. They're identical twins. They're the same size and shape. Okay, so let's look at an example. If we look at these two triangles here, can we describe this as a rigid motion? So remember, rigid motion didn't have to do with position. They can be in a different place, but they should have the same size and shape. And if we're looking at these, this triangle is very skinny, and this triangle looks almost equilateral, right? And so no, because they are different shapes. So what I'd like you to do is down at this image, I'd like you to say whether or not each of these images represents a translation. Are these copies of each other, identical copies of each other? Are these identical copies of each other? And are these identical copies of each other? So for this first one, we can look at these airplanes, and if I were to slice this airplane out and move it right over top this other one, they would be exactly the same. And so, yes, this is a translation because they are each the same size and shape. And I do want you to write that whole sentence out. Are these a translation? Well, if I cut out this image here and I just dragged it over, they wouldn't overlap perfectly. This is actually a different type of transformation. This is a reflection because it's the same shape, but it has flipped, right? This person has her right hand, well, her left hand up. This person has her right hand up. So this is no, they have opposite hands raised with the cape. And this last one, again, looking at it as the image, if I was walking down the street and this was my point of view, I might say these are probably all the same size and shape. However, in this image, no, they are not, because this one in front is a lot bigger than this one in the back, because they have different sizes. Okay, so from a real world perspective, these pillars are probably all translations of each other, but in this image, they are not because they change sizes. Let's take a look at the next page. So in this example here, we'd like to actually translate the figure. So what we're going to do in order to move this triangle is we're going to move the three vertexes one at a time. So our first step, we're going to take the pre-image or the original point I, that's this one up here, and move it 7 units right. So we're going to take it and we'll go 1, 2, 3, 4, 5, 6, 7 units right and 3 units down. 1, 2, 3. So we went 7 right and 3 down. And this we'll call I with a little apostrophe. We say I prime. I prime. And then we're going to find our other points. So we're going to do the same thing for point J, 7 to the right and 3 down. So 1, 2, 3, 4, 5, 6, 7 to the right and 3 down. And that becomes J prime. And then we'll do the same thing for H. 2, 3, 4, 5, 6, 7 to the right and 3 down gives us H prime. And then if we connect those 3 points, that is our new triangle. So in order to label those points, we've called them by their original name with a little apostrophe that we say prime. So our pre-image was those 3 points. Our image, the result, our new point instead of H is H prime with the coordinates 1, -2. J became J prime with the coordinates 5, -1. And I became I prime with the coordinates 3, 3. And I've actually just realized I miscounted. I prime should be here at 4, 3. See, I counted over 7, but then I went back 1 by accident. So this should actually be 4, 3. How did I notice that mistake? Well, because this moved 7 to the right, which is 7 in the positive direction, right? On the number line, when you move right, that's like adding. If I take the original X, I can add 7 to get the new X value. Add 7 to get the new X value. So moving to the right is adding to the X value. And then moving 3 down, well, down is our negative numbers. So that's actually going to be subtracting from the Y value. So I take my original Y value, -3, -3, -3. And so you can either compute it algebraically and plot the new points, or you can move things geometrically to find the new points. There's 2 different ways to find those. So what do we notice about all of the side lengths and angles of our new image? So this new triangle here compared to our original triangle. Well, if we look at the distances of each of these legs, because I just essentially took this triangle and moved it over, all side lengths and angles are congruent to the original. Another way we can say that is triangle HIJ is congruent to triangle H prime I prime J prime. So how do we write this transformation? Well, if you look at how we calculated this, we added 7 for our X value and subtracted 3 for our Y value. So when we calculated it from our points algebraically, what we did is we added 7 to the X and subtracted 3 from the Y. And the way that we write this in function notations is we write a T for transformation, and then these little pointy brackets. And in the future, we'll refer to that as vector notation. So we can call this a vector because it's got the pointy brackets. That means it's going to be a movement. X was a +7 change and Y was a -3 change. So just like writing a point, but this means that it's not the point on the graph. If I look at the point 7, 3, or 7, -3, there's no point there, right? There's no point at that point. However, that's the distance that we moved all of the points. The distance from 0 to that point is the same distance that we just moved all of these points. Okay, so if we look at our notation here, if A is positive, it's moving to the right. If A is negative, it's moving to the left. So if I'm moving to the left, my x value, or a value, will be negative. If b is positive, it moves up, and if b is negative, it moves down. So let's practice this notation. For this first part, we want to write a translation 15 units to the left and 24 units up. So to the left is a negative direction. So we're going to say this is a transformation 15 units to the left, which is in the x direction. X always goes first. 24 units up, and that's positive. So then this becomes positive 24. You don't have to write the plus sign. So we would simplify this just to say the transformation of negative 15 and 24. And notice the little brackets are a subscript. They're down below the level of the t. So you have to use a special notation when you're putting that in as an answer, or make sure when you're writing it in your notes, you're writing it below the level of a t. Kind of like how an exponent goes up, that transformation, the vector part, goes down. Let's do one more. A translation, right 8 units to the right is positive, and down 4 units. Down is negative. So think about when you're looking at your graph, when you're looking at a grid like this, up is the positive numbers, down is the negative numbers. To the right is positive numbers, to the left is negative numbers. So those are the same values that we're using when we're moving these points as well. So this is a transformation, subscript, vector notation, the pointy brackets. It's the same symbols as less than or greater than. So we're doing right 8 units, that's positive 8. Make sure you always do right and left first. Even if it was listed second, we move it first. And then down 4 units is minus 4. Always x direction and then the y direction. In example 3, we're doing something a little bit different. We're given the transformation and we want to move that point. So remember up above, when we were moving the point, we just added it to the transformation. Negative 6 plus 7 gave us positive 1. 1 minus 3 gave us negative 2. Okay, so here we have a 0.65. We want to translate it by negative 3, 1. So we're just going to put that transformation directly underneath and imagine there's like a little wall. And that's going to give us our new x and y values. 6 minus 3 is 3. 5 plus 1 is 6. So that gives us our new point, p prime, 3, 6. So the x values together made the new x value. The y values together made the new y value. Let's do another one, okay? This time we're doing it backwards. I'm given point K, and it's translated to point P. So think about P is basically K prime. Write a function notation rule for the translation. So we went from 4, 6, and we ended up at 7, negative 2. And we want to know what goes here. Okay, well, if we're adding backwards, that's the same as subtracting, right? So if I say 4 plus what is 7, 4 plus what is 7, that's the same as 7 minus 4, which is 3. And I can say 6 plus what is negative 2. 6 plus what is negative 2. So that means negative 2 minus 6, which is negative 8. And so our transformation, subscript 3, negative 8. So we have the point, we have the transformation, and we have the new point, which in this case had an also new name called P. Okay. In our next example, we want to plot some images. So we have the original H, B, Q, N. After the translation, negative 2, 5, and list the coordinates. So this is the pre-image. Our original point, H, is at negative 1, negative 3. B is at 1, negative 3. Q is at 4, negative 5. And N is at negative 1, negative 5. And then we want to move them, and we want to move them by negative 2, 5. So that means left 2, up 5. Left 2, up 5. There is H prime. Left 2, up 5, n prime. Notice h to n was 2 units vertical. H prime to n prime is still 2 units vertical, which means in order to find b prime, I can also do 2 units left and 5 units up, or I can say from h to b is 2 units to the right, so h prime to b prime is also 2 units to the right. So using that idea that the distances have stayed the same, these shapes should still be congruent. So I can apply that same idea. From n to q, I would count 5 units to the right. N prime, 5 units to the right, should be q prime. Notice if I count from q, 2 units to the left and 5 units up, it's the same point. And that gives us this trapezoid. So what is the coordinate of h prime is now -3, 2, which notice if I take -1 minus 2 is -3, -3 plus 5 is 2. So it's still following our algebraic rule as well. B is at -1, 2. Q prime is at 0, at 2, 0. And N prime is at -3, 0. Okay, now for number 6, what we're doing is identifying what is the transformation that happened. Well, we know we're going from M to M prime. So just pick one of the points and look for the transformation. So if we're choosing to pick M, always in the X direction first, we moved all the way here and then there. So how far did we move in the X direction horizontally? We moved 2, 4, 6 units. So that gives us a -6 movement. And then we moved from there up 4 units. Up is positive, so we're looking for the transformation by -6, 4. So I'm looking here, the transformation by -6, 4 is C. It moved to the left, that's in the negative direction, and up, which is in the positive direction. Always X before Y, so just like plotting points. Let's look at a few more examples. On the next page, example 7, we want to plot the image of the triangle DZR after the translation by -4, 2, and list the coordinates of the image. We've done one similar to this, so I'm going to let you try this, and then we'll go over it together. So I'm going to start by putting the coordinates of our original points, the pre-image. D is at 0, 0. Z is at 4, 3. And R is at 2, 0. To find our new points, D prime, I'm translating it by -4, 2. So this is X direction, Y direction. -4 is 4 units to the left, and 2 is 2 units up. So if I take D, move it 4 units to the left and 2 units up, there is D prime. And the coordinates there are at -4, 2. For Z prime, let's do this the algebraic method. I would take 4 and I would put the vector right below it, -4, 2. 4 minus 4 is 0. 3 plus 2 is 5. Why did I use subtraction for the first one and addition for the second one? Really, I'm adding both of them. But our X coordinate of our vector is negative. So it's 4 plus -4, which is why I said minus. So plotting the point 0, 5, right there, there is Z prime. R, I'll use the vector method again. So the algebraic method, -4, 2, placing the vector below. 2 plus -4 is the same as 2 minus 4, so R prime is at -2, comma, and then 0 and 2 gives us 2. So that's -2, 2. And notice D to R, 2 units directly to the right, D prime to R prime, directly 2 units to the right. So there's 3 different ways that you can find these points. For number 8, we have triangle ZKW is translated to triangle GRM. So this is the pre-image and the image, the original and the result. So label the pre-image. The pre-image is this one. Pre-image. Triangle ZKW. Describe the transformation, the translation, in function notation. So you're going to pick one of the points. Now, because we know this was just moved, we can say I'm picking the top point. That would be Z, moving to G. Just like when we plot points, we go sideways first. So this goes directly over G and then drops down to G. Similar to like finding slope of a line, how you make that triangle, counting the same way, we're going to go 3 to the right, so that's positive. And then we go 4 down, so that's negative. So we have our translation by 3 to the right and down 4. On number 9, Ernie started to complete the translation below but didn't finish. Describe the translation in function notation. So I know that S becomes S prime. So again, just like making slope, we'll go sideways first, and then we go vertically. So we say, how far sideways did we go? We went 2, 4, 5 to the left. So to the left by 5 is negative. And then we went up by 5, which is positive. So that's the translation by -5, 5. Complete the translation and label point P. So again, we're going over 5, up 5. There is point P prime, but we also have a segment there, so we have to draw in the segment for the transformation or the translation to be complete. Translation is a type of transformation. So we'll be learning other types of transformations as well. For number 10, a translation sends square T onto square R. Where does this translation send point X? So just like before, we're going to pick a point and see where that translation takes us. So any point on the square, I'll pick the top right point, should go to the top right point. And so we go sideways first, 3 to the right and up 1. And we're not writing this in transformation notation, but if we were, it'd be the translation by 3 and 1. Really what we just want to do is do the same thing to X. So we go 3 over, 1 up, that takes us to point B. Okay. I mentioned that there are other types of transformations. So here are a few other types of transformations. We've just seen translation. Translation is just moving an object. So here's an object. If I move it, that's a translation. Notice I didn't turn it. I didn't flip it. I just moved it. So it was here. Without turning it at all, I move it somewhere. That is a translation. A reflection is when I have something and I flip it. So the image that we saw earlier with the cape, that is a reflection. Think about on your phone when you're taking a selfie, if you have makeup on your right side of your face, in the selfie it looks like it's on the left side of your face, right? That's a reflection, okay? And then a rotation is when I take something and I just turn it. So that's a rotation. Now I don't have to turn it around itself. I could take it here and turn it around this point, kind of like an orbit. That's also a rotation. But for part A, we can tell it's not a translation because point D was on top and now point R prime is on top. But if I look at this, these are 2 units apart, 2 units apart. This goes 2 and 1, 2 and 1. So it's the same shape, but what happened is it rotated. So RDL, RDL, this is a rotation. If I took a picture of RDL and I moved it, I would have to rotate that picture. Okay, B is not rigid, not rigid. It changed size. Part C, this one is I could just take that triangle and move it directly between those two. And so this is a translation. And then for this, it looks like a mirror, right? I had this triangle and it flipped. And so that is a reflection. Let's take a look at section 2. For section 2, we're looking at reflections. Our objective is to find the reflection of images. So how do we do this? So instead of using tracing paper, we are just going to practice doing this by hand, which is how most people do it anyway. So if we want to reflect across an axis, what we're going to do is we're going to create a line that's perpendicular to that axis. So what do I mean? If I want to reflect across the x-axis, I'm going to draw a bunch of vertical lines. And specifically, I want vertical lines from my point across the axis, and then I want to create that same line again below the axis. So this is 2, 4, 6 units. Then I want to create 2, 4, 6 units, and there is L prime. And then M, 2, 2, there is M prime. Now N is a special case because the distance from N to the x-axis is 0, and therefore it just stays. And that is N prime, doesn't move because it was already on the line of reflection. And so here we have our triangle, M prime, N prime, L prime. So for our image, point M started at 1, 2, and it moved to 1, negative 2. Okay. N started at 7, 0, N prime is at the same point, 7, 0. L starts at 5, 6, and it moves to 5, negative 6. If you'll notice, this was across the x-axis, and the x values did not change. Okay, so when I reflect across the x-axis, the x values don't change. If we reflect across the y-axis, this time it's the y values that won't change. And so we're going to do the same thing. We're going to find our line of reflection. That's our y-axis here. And we're going to create lines that go perpendicularly to it. So this is a vertical line. We're going to create horizontal lines. From M to the y-axis, that's 1 unit. So I go 1 unit on the other side. There is M prime. L, 2, 4, 5. 2, 4, 5, there is L prime. And then N, this time it's not on my line of reflection, so I do have to reflect it. 2, 4, 6, 7 units. And so it goes 2, 4, 6, 7 units. There is N prime. And so here is our triangle. And if we plot those points, M prime is at negative 1, 2. N prime, negative 7, 0. L prime is at negative 5, 6. So again, the y values, across the y-axis, the y values did not change. What's nice about this is that when we're reflecting across an axis, the algebraic way of telling what our new coordinate would be, we're not adding or subtracting this time, we're multiplying by just a negative 1. So if we look back at our original example here, the x values don't change, but the y value changes sign from positive 2 to negative 2. N, the x value doesn't change. My y value in this case also didn't change because positive and negative 0 are both just 0. L, x value doesn't change, y value changes sign. Across the y-axis, now our y value doesn't change, but our x value goes from positive to negative. Same thing here, y value doesn't change, x value changes from positive to negative. And if we had a negative x value, it would change to positive. And then same here, y value doesn't change, x value changes from positive to negative. So what we can say is if we are reflecting across the x-axis, the x value doesn't change. X stays itself, but the y value becomes negative. If it was positive, it's negative. If it was negative, now it's positive. If we're reflecting across the y-axis, the y value doesn't change, but the x value becomes negative. So again, if it was positive, now it's negative. If it was negative, now it's positive. So let's try these examples. Use function notation for the reflections. If point P, 3, negative 5, is reflected across the y-axis, what are the coordinates of its image? Reflection big R across the y-axis. And then we can say point P becomes P prime. Y-axis, the y value doesn't change. The x value changes from positive to negative. On number 2, if k, -6, -8 is reflected across the x-axis, what are the coordinates of k prime? Using function notation, we'd say the reflection across the x-axis yields k prime. X-axis, the x value stays the same. The y value changes sign. So this is negative becomes positive. Let's look at some more examples. Triangle QRT has vertices. Q is at 6, -1. R is 2, 0. This is Q. R. T is 1, -5. T. If the triangle QRT is reflected across the y-axis onto triangle MAP, so that says Q goes to M, R goes to A, T goes to P. Then which of the following coordinates are coordinates of triangle MAP? Okay, choose all that apply. So we want to reflect this across the y-axis. 2 units, 2 units. R becomes A. Q, 2, 4, 6, 2, 4, 6. Q becomes M. So just like when we were doing our similar triangles, the first letter becomes the first letter, second letter becomes the second letter, and so T, our third letter, 1, 1, becomes P. Here's our triangle. Which of these are on our triangle? Well, -6, +1, no. 2, 0, yes. -1, -5, yes. -6, -1, yes. In our next example, if segment KT is reflected so that K, 1, 6, maps to K prime, 1, -6, then T, which is -4, 5, maps to T prime at, if K goes to K prime, that was across the x-axis, right? We can double check. 2, 4, 6, that was a distance of 6. 2, 4, 6. This is also a distance of 6. So how do you know where the mirror is, where the line of reflection is? It's halfway between those points and perpendicular to that line. T prime will be 2, 4, 5, 2, 4, 5. T prime. So that coordinate is -4, -5. Again, we could also use algebraic. Across the x-axis, the x value doesn't change, the y value does. Our line of reflection is the x-axis. Okay, let's look at graphing horizontal and vertical lines. If we graph the line x equals -2, what we want to do is we want to say, where is x -2? So here is one place that x is -2, but I could pick the point -2, 1, or -2, 4, or -2, -2, right? All of these points have an x value of -2. And so we have a vertical line at -2. So if we want to reflect the point -4, +1 across this, then what we have to do is the same thing we were doing before, 2 units to get to that line, 2 units away from that line. And so here is our new point. So if we call this K, then K prime will be at 0, 1. Okay, so again, creating that perpendicular line. Okay, we want to graph the line y equals 1, so I find the point where y equals 1, which on our axes would be right here. But then there are also the points 1, 1, and 2, 1, and -3, 1. And so all of these points have a y value of 1, so we have a horizontal line. And then we want to reflect 0, 2, 0, 2 across this line y equals 1. So we're going to say from this point to our line is a distance of 1. So our reflected point has a distance of 1. If this is point P, then P prime is 0, 0. A few more examples here. The vertices of triangle MAN, 3, negative 2, 1, negative 3, 4, negative 4. Triangle MAN. Graph the image of triangle MAN after reflecting across y equals negative 1 and list its coordinates. Reflect across the line y equals negative 1. Well, where's the line y equals negative 1? First, I find the point where y equals negative 1, and then I'm going to draw my line. I'll draw it dashed so that we can tell it's a mirror. And then I'll move my points. So M, 1 unit away, there will be M prime. A, 2 units, 2 units. There will be A prime. And N, 3 units, 3 units. And there will be N prime. So M prime is at 3, 0. A prime is at 1, 1. N prime is at 4, 2. Okay, if we look at another section here, or another question here, the endpoints of segment MY are at negative 1, negative 2, and 4, 2. Let me draw my M here. There's MY. If MY is reflected across the line x equals 2 would go here. And this is why it's nice to have that dotted line so we can tell which line we're reflecting and which line is the mirror. Okay, graph and list its coordinates. So let's start with M. 3 units over, 3 units over. There is M prime. And then Y, 2 units over, 2 units over. There is Y prime. Notice that these two lines cross on the line of reflection, on the mirror. So we have that M prime is 2, 4, 5, negative 2. Y prime is at 0, 2. Let's continue some more examples. On part 3 here, we want to graph the image of triangle JNZ after reflect across x equals negative 2. So we say, where does x equal negative 2? Here. And all of these points. And so point Z is easy. It's on my mirror. It doesn't move. Z prime is the same point as Z. N, 2 units away. N prime is 2 units away. So I counted 1, 2 units to my mirror, 1, 2 units away from my mirror. J, 2 units away from the mirror, 2 units away from the mirror, J prime. So here is the image. List the coordinates of each. We'll list them in the same order, J, N, Z primes. J prime is at 0, negative 5. N prime is at 0, 0. Z prime is at negative 2, 0. Sometimes if you have too many lines, it's hard to see where your origin is. It might be just nice to mark with a different color. There's your axes, so you can see where your origin is. That's where you're counting from for your coordinates. On number 4, graph the image of triangle DFG after it is reflected across the y-axis. So reflecting across the y-axis, let's start with D, F, and G's original points. That's at negative 3, 1. F is at negative 2, 4. G is at 2, 3. D prime, F prime, G prime across the y-axis. There's my mirror. F is 2 units away. F prime is 2 units away. So that's at 2, 4. The y value did not change. The x value switched signs. G, 2 units away, 2 units away. G prime is at -2, 3. D prime, we can do the algebraic method. The y value will not change. The x value will. Should be at 3, 1. If we do it the counting way, we could say D is 3 units away. 3 units away is D prime. Okay, so again, we have multiple ways of doing these reflections, but really only when it's reflecting over one of the axes. There's a way to do it for the other lines, but it's a little bit more complicated. And again, where they cross, the points of intersection should be on our line of reflection. Okay, so for this example, we have quadrilateral UTNA mapped to triangle HRSG. Is this a rigid motion? Well, is it the same size and shape? Yes. I can take this and this, they're exactly the same size and shape. Yes. Same size and shape. In your own words, describe the transformation. So if I'm describing this in my words, I would say this quadrilateral has been moved up and to the right slightly. The quadrilateral has moved up and slightly right. If GS is 14 units, UA is y plus 1 units, AN is 2y plus 4 units, find the value of y and explain. Well, remember we said same size and shape means the sides and angles should be congruent, which means they have corresponding pieces. So just like we were doing with our triangles before, we're going to look at which piece corresponds to which piece here. So GS, if we look for GS here, corresponds to NA. So we can set those equal to each other. GS, which is 14, equals AN or NA, which is 2y plus 4, because of corresponding congruent parts for rigid motions. So to solve for y, -4, 10 equals 2y, divide by 2, y equals 5. In the next one, we have a triangle JEG reflecting onto KML. If GE is 18, JG is 20, LM is x plus 5, and MK is x, draw in the line of reflection and write its equation. So remember I said in order to find the line of reflection, we look halfway between the points. So halfway between G and L is this point here. Halfway between E and M is this point here. So that gives us our line of reflection through those 2 points. So our line of reflection is at y equals 1. Is halfway between the reflected points. What is the value of x and y? Well, again, we have corresponding parts. So if EG is here, it would reflect onto, well, G goes to L, E goes to M. So EG corresponds to LM. That means EG equals LM. Well, EG is 18. LM is x plus 5 minus 5, x equals 13. Again, because corresponding parts are congruent for rigid motions. What is the perimeter of LMK? Well, we know that this is 18. We also know JG corresponds to LK, so this is 20. And now we know that X is 13. So we can say 18 plus 20 plus 13 equals 51. No units were given. Okay, let's take a look at section 3. Our last section for today is rotations. That was our third type of rigid motion. And our objective is to identify rotation images of figures and draw them. So a rotation is a circular movement of an object around a fixed point of rotation known as the shaded figure has been rotated clockwise about the origin. Label the degree of rotation for each figure from the shaded figure. So this is the one that's shaded. If I rotate, I always rotate counterclockwise. So think about when I'm drawing angle measurements or something, I'm measuring usually from the positive x-axis. So we always say this is quadrant 1, 2, 3, 4. So we're always counting in a counterclockwise manner. So when I'm rotating, I'm also going to rotate in a counterclockwise manner. So I can say this has been rotated 0 or a full 360 degrees. Remember, 360 degrees means going all the way around. I can say then that to rotate by one quadrant is a right angle. So that is by 90 degrees. 2 quadrants is a straight line. That's 180 degrees. 3 quadrants is 180 plus one more 90 makes 270 degrees. And then all the way around is 360 degrees. So determine the number of quadrants moved per degree rotation. Well, 90 degrees is 1 quadrant, 180 is 2, 270 is 3, and 360 is 4 quadrants, which is the same as saying no quadrants. So it'll be in the same quadrant. Let's look at some examples. Again, we won't be using tracing paper for this, but again, originally we never had tracing paper to practice this back in my day. So we'll practice rotating. If you have tracing paper, you're free to use it. You're welcome to use it, but you won't be able to use it on assessments. So we'd like to rotate the points, the point given, point H, using the origin as the point of rotation. So this is where we're rotating about, using the perpendicular slopes. Okay, so let's start with point H, and we're going to call it -2, 3. We're going to put it directly on that point, -2, 3. Okay, so our 0 degree rotation, our point will stay the same, -2, 3. The other rotation that the point stays the same will be 360 degrees, -2, 3. Okay, because if I rotate nothing, I don't change it. If I rotate 360 degrees, I go all the way around back to the same point. Now, if I was to look at the slope to the origin, so make a line to the origin, what is that slope? Well, slope is rise over run, so that'd be 3, 2. 3 over 2. If I rotate by 90 degrees, I take this, imagine rotating it by 90 degrees. Well, this triangle here, that's on the y-axis, now rotates. So it was on this axis, now I'm rotating it 1 axis over. So this went 3 on the axis, this goes 3 on the axis. So notice I'm drawing the same triangle, and I'm starting with how far along the axis was it? And drawing that line first. So my new coordinate here, 90 degree rotation, is at -3, 2. And my slope now is rise over run, -2 over -3. -2 over -3. And actually, I made a mistake. Rise over run, 3 over -2. So now I have rise over run, -2 over -3, or you can count from this way, +2 over +3. Another way to write this is 2/3. Okay, now if you'll notice, these two slopes are reciprocals and also opposites. They are perpendicular. If you remember from algebra, when we have perpendicular slopes, they multiply to -1. 3 over -2 times 2/3 equals 6 over -6, which is -1. So these are perpendicular. Opposite reciprocals. Perpendicular lines have opposite reciprocal slopes, negative and flipped. Okay, let's rotate again. So again, still going 3 along the axis. Our next rotation goes into our next quadrant. Our coordinates here are 2, -3. Our slope is rise -3, run 2. -3 over 2. This is the same as our original slope. These two lines are parallel. Equal slopes are parallel. And then our last one, still going 3 along the axis, rotating to the last axis here. My triangle goes 3 and 2. So my slope here is rise 2, run 3. 2 over 3. Or you can count it as -2 over -3 again. Our coordinates here in our last quadrant are 3, 2. If we were to call these points by name, we started with H. Our next transformation, our rotation, would take us to H prime. And then we do another transformation. So we have H prime prime or H double prime. And then we do it again, H prime prime prime. We've changed it 3 times. We call that H triple prime. So we have H, H prime, H double prime, and H triple prime. Let's do another example. Rotate point P using the origin as the point of rotation. Using tracing paper, we're not using tracing paper. Okay, so what we're going to do, again, we're going to draw our triangle for point P. That is at 4, 1. And then we'll use our axes. So I started on this axis. Rotating 0 degrees stays on the same axis. So my point is still 4, 1. 360 degrees will be the same, 4, 1. 90 degrees, move by 1 axis. So from here, 1 axis. 4 units, 4 units. Draw my triangle. My new coordinates, that's P prime, are -1, 4. We rotate again, moving 1 more axis over. That is 180 degrees of rotation. Draw my triangle again. We are now at -4, -1. And our last rotation for this is 270 degrees. 4 units on the axis. Draw the same triangle. So notice 4 units along the axis gives me that reference point every time. 1, -4. So what are our patterns here? Well, when we're rotating by 90 degrees, so we rotated by 90 degrees, our X and Y values switched and X became negative. So X and Y switch and our new X value became negative. So this one is 90 degrees. When we rotate by 180 degrees, that's these ones, our X and Y values switch and both become negative or opposite. So now we're in the original X and Y values, our original X and Y values, except the opposite. So this will be -X, -Y. That is 180 degrees. For 270 degrees, again, our X and Y's switch, which means they're the opposite of our original XY. And the sign for just the Y value has changed. So this becomes Y, -X. That is 270 degrees. And for 360 degrees is our original point x, y. So these are all with your original x and y values. Let's look at some more functions or some more examples. For our rotation notation, we use a little r. Remember, big R was for reflection. Little r is for rotation. A rotation, x degrees around point C, where x is the degrees counterclockwise, always going this way, this way, this way, this way. So I can't say it's to the left because depending on where you are in this rotation, it's always counterclockwise, but it's not always left or right. And C is the center or the point of rotation. So let's take a look at this example. Perform the rotation R 90 degrees around O. O is the origin. So here's our center point. I want to take point N, 90 degrees. Here is N prime. Here's point E. Here's my triangle. 1 unit along. Here's my new triangle. 3 units. 3 units. There is E prime. Point T. Here's my triangle. 4 units along the axis. 4 units along the axis. 2 units in. There is T prime. 2 more units in to get L prime. I'm going to highlight my final transformation so that I can say this is the final quadrilateral. Now, you should be doing this in pencil. So what you can do after you've drawn your rotation is go back in and erase some of those triangles. So the next one, I'm actually going to do it in pencil. Our image, L prime is at -4, -4. The pre-image is actually typed wrong. This should be -4, +4. Point T prime is at -4, -2. N prime should be the switch, 1, 0, and this becomes negative, -1, 0. And point E, again, they switch, 1, -3, and our first one becomes negative. And we can confirm that, -1, -3 by our rotation. Okay, in the next example, we want to rotate XG by 90 degrees. So I'm going to do this in pencil so that I can draw the triangles and show you how you should erase them. So if we start with point X, my triangle could be this one. Rotating by 90 degrees tells me 2 units onto my new axis, and then 3 units away. How come I didn't count by this one? Well, that's not an easy number to count by, right? So 2, 3, I'm going to count by the integers, 2, 3. There is X prime. And then I go in with my eraser, and I erase everything except for that final point. And then I'll do G. So here's my triangle for G. That's 4 units along the axis, 4 units along the axis, 2 units in, 2 units in. There is G prime. So there's my triangle that was rotated, but then I'm going to go back in and erase it so that all I have left is my segment that was rotated. I think it turned out dark enough. I'm sincerely sorry if it wasn't dark enough to see. I'll use pen for the rest. So for number 3, we want to rotate this triangle 180 degrees clockwise, that's backwards, about the origin, okay? Now, the nice thing about 180 degrees, clockwise and counterclockwise will give you the same rotation. 180 and 360 are the only ones that do that. So if I take point W, rotate that 180 degrees, so here's my triangle. I'm rotating it not 1, but 2 axes away, 3 units, and this went this way. So again, rotating, it goes this way. there is W prime. Point I, here is my triangle. Not one axis, but 2 axes away, 3 units. It went this way, so it will go this way. And there is point I prime. Notice point Z, if I'm rotating, remember clockwise and counterclockwise are the same, but point Z, it already kind of gave me my triangle there. That's 1 unit away, 1 unit down, going clockwise or counterclockwise will give me the same point Z prime. And so my final result is this triangle, W prime, Z prime, I prime. Okay, I'd like you to try this next example and then we'll run through these two together. For triangle RHS, it's rotated 180 degrees around the point -2, 1. -2, 1, right here. So what am I going to do? I'm going to draw in some fake axes. Here they are. And I drew them in pencil because I am going to erase them at the end. So here's point B, rotated by 180 degrees. It's on the axis. So when I rotate it, 2 units away from my blue point, 2 units away from my blue point, there is, it's supposed to be an R. R prime. Point H, 1, let's see. Here would be my triangle. So rotate it by 180 degrees, so it goes all the way around, 2, 1, there is H prime. And then point S, here's my triangle. I rotate 180 degrees, 2 units along the axis, there is S prime. Okay, there's a lot of lines going on here, so I'm gonna go ahead and erase my penciled in axes. Hopefully it doesn't smudge my pen too much. This is why I always say work in pencil. Okay, so my final triangle will be here. Okay, it says what are the coordinates of S prime? S prime has the coordinates -4, +2. For number 5, quadrilateral DUNV is rotated 90 degrees counterclockwise about the point 1, 3. 1, 3. There's my center of rotation. What are the coordinates of D prime? So this time I'm not going to rotate all of them. I'm just going to rotate point D. So point D is 3 units away directly on one of what would be the axes through that point. And so 180 degrees would be the opposite, but we just want to go 90. 90 is just this way. So 3 units away, there is D prime. So the coordinates there are 4, 3. It's not an option, so I'm going to write it in here. E, 4, 3. It was supposed to be this one, but that's been a typo that I just keep forgetting to change year to year. Let's take a look at our last page. So for this example here, we want to label the pre-image. So how do we know which one is the pre-image? It's the one that we started with, the one without the primes. So this is the pre-image triangle IVY. Connect Y to Y prime, Y and Y prime to the origin to find the angle of rotation. So again, you should use a straight edge for this, but I'm going to actually use my straight edge. Okay, so Y and Y prime. So what is the angle of rotation? This angle here. Well, you can see it makes a straight line. So the angle is 180 degrees, about 0.00. For number 2, again, we want to label the pre-image. It's the one without the primes. This is the pre-image A, B, C, D. Describe the transformation. Well, if we look from A to A prime, that looks like A 90-degree rotation about the origin, and rotation is the little r. How did I know this wasn't a transformation that was a translation or a reflection? How did I know this was a rotation? Well, I didn't just slide this, and I didn't flip anything, right? If I flipped it, then AB going this way would then become AB going this way. But it's still AB going the same direction. So we can talk about orientation from A to B, points the same direction. This is counterclockwise, this is counterclockwise. Then it has to be not a reflection. Okay, we are going to do this as an activity in class, so don't work on that quite yet. I know this was a long notes video, but it's kind of, these three really go together as our rigid motion transformations.